Hello, in this video I would like to talk about number systems with the three different bases. In our daily life, we use the decimal system and we feel most comfortable with a decimal system. In the decimal system, we use 10 different numerical symbols, including 0, 1, 2, 3, and until 9. However, in case of computers, the decimal system is not necessarily very natural to represent a collection of binary digits. To represent the states of binary digits, usually we use a binary system. The binary system includes two numerical symbols, 0 and 1. But however, the zeros and a lot of zeros and ones can be very difficult to read and remember for human beings. So we actually use a hexadecimal system. The hexadecimal system includes 16 different numerical symbols, including 0, 1, 2, until 9, and then alphabet A, B, C, D, E, F. And A represent a numerical value 10, and B represent a numerical value 11, C 12, and so on until F represent a numerical value 15. The binary digit is also known as the bits. So we use a term a bit a lot. So now the question is how many different states can you represent using n number of bits? All right. So for example, if you have a 1 bit, you can take you can take only 0 and 1. So you can represent 2 states using 1 bit. So if you have 2 bits, then we can have 0, 0, 0, 1, 1, 0, 1, 1. So we can take 4 different states. So if you have a 3 bits, and then we can take 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on until 1, 1, 1. So we can have 8 different states. So when you have an n number of bits, then you can represent a 2 to the nth power number of states, because it's going to be 2 times 2 times 2 times 2 times 2 times 2 times until you hit this one. So so if you have a 4 bits, then you can represent the 16 bits, because we can take 2 different states for each bit. So 2 times 2 times 2 times 2 times 2, so which will be 16. And one of the numbers I want to remember for computing from now on is this number, 2 to the nth power. 2 to the 10th power, So 2 to the 10th power is a 1024. This is a very convenient number, so I want to remember it. So again, I want to remember this very convenient number, 1024, which is 2 to the 10th power. This one also we represent as a k. So we'll get back to this issue again at the last slides. Okay, let's talk about how to convert a binary number to a decimal number. On the next slide, we'll talk about converting from hexadecimal to a decimal number. All right, so let's look at the 8-decimal number and how it means. Okay, for example, if we have some decimal number like 357, so what that means is we have 3 100, and then a 5 tens, and 7 ones. So that is 300, and then this is 50, and it's going to be 7, so it's 357. So in case of a decimal system, we use base 10, so base 10. And when you calculate, as you can see over here, the exponent are starting from 0 and 1 and 2. In case of a binary system, basically works the same way. Only difference is base will be different. So this time base will be 2 rather than 10. So for example, if we have a binary number like 1101, so if you change it to a decimal number, we can use the base 2. And just like over here, now we use a exponent starting from 0. So 2 to the 0th power, first power, second power, and third power. So 1 is 2 to the third power, 1 times 2 to the third power. And next one is 1 times 2 to the second power. And next one is 0, so we don't have to worry about it. And the next one is 1, so which is 2 to the 0th power. So this will be 8, this will be 4, and this will be 1. So if you add them, then you have 13. So 1101 in binary is 13 in decimal number. So let's look at another example. How about 1101? So if you have a 1001, so it is what? Starting from 0, 1, 2, 3. So that is 2 to the third power plus 2 to the 0th power, which is 1. So 8 plus 1, so that will be 9. How about the next one? 110011. Again, we just look at the position here. So 0, 1, 2, 3, 4, and 5. So 2 to the 5th power, and plus 2 to the 4th power, and 2 to the 1st power, and 2 to the 0th power. So if you add them, so this will be 32, this will be 16, this will be 2 and 1. So if you add all these numbers, it's going to be 51. So hopefully it makes sense to you. Why don't you work on this one, 1111. And okay, well, let me go over that one more time. So 1111, so it's going to be 0, 0, 1, 2, 3. So 2 to the third power plus 2 to the second, 2 to the first, and 2 to the zeros. So this will be 8, 4, 2, 1. So if you add these numbers, it will be 15. Okay, so why don't you work on this and do some more practice, and also I'll provide a homework for all these conversion questions. Okay, now let's take a look at converting from hexadecimal number to decimal number. If you remember, hexadecimal number uses 16 different symbols starting from 0, 1, 2, 3 all the way to alphabet F, and F represents 15. Alright, so let's take a look at the example here. So here, just like in the previous slide, only difference is we use a different base. So this time we are using a base 16 rather than a 10 in case of decimal system, and 2 in case of a binary system. Alright, so how about this number 3a? So when you have a 3a, so again we start from a 0 in terms of exponent, and then 1. So this is 3 times 16 to the first power plus, remember a has a numerical value 10, so a is a 10 times 16 to the 0th power. So this will be 48, and this will be 10. So if you add those numbers, it will be 58 in decimal number. How about this ABF? Again, we start from a 0 for exponent, so 0, 1, 2. So it's going to be 16 to the second power, and a has a numerical value 10, so 10 times 16 to the second power. And b has a numerical value of 11, so 11 times 16 to the first power. F has a numerical value 15, so multiply that by 16 to the first power. So if you add these numbers, and then you will have 2751 in decimal. Okay, how about one more example? How about FF? So again, F has a numerical value 15, and this one is so we start from a exponent 0 and 1, so 16 to the first power, and F is again numerical value 15, and multiply that by 16 to the 0th power. So FF in the hexadecimal is 255 in decimal. Okay, one more example. How about 35F? So just like we did, this will be 3 times 16 to the second power plus 5 times 16 to the first power plus F has a numerical value 15, so multiplied by 16 to the 0th power, so that will make 863. Okay, how about the next example? C D5. Let me save this for your own practice. Okay, now let's think about how to convert a decimal number to a binary number. Alright, so for example, 35. To convert 35 to a binary number, what you need to do is we divide 35, divide 35 until you keep dividing a number by 2 until the quotient becomes 0. So let me give an example. Okay, so like a 35. So if you divide the 35 by 2, the quotient will be 17, and the remainder will be 1. Okay, and if you also divide, you divide the 17 by 2, the quotient will be 8, and then a remainder will be 1. And if you divide 8 by 2, then quotient will be 4, and remainder will be 0. If you divide 4 by 2, quotient will be 2, and the remainder will be 0. If you divide 2 by 2, quotient will be 1, and the remainder will be 0. And if you divide 1 by 2, quotient will be 0, and the remainder will be 1. Okay, and now you collect these remainders this way, and then there will be the binary number. So in this case, it's going to be 1 1 0 0 0 1 1. So 35 in decimal will be 1 0 0 1 1 in a binary number. Okay. All right. So let's look at another example. How about 95? So if you do a 95, again, you keep dividing this number by 2 until you hit 0. And then you collect all the remainders this way. Okay. So it will be, if you divide 95 by 2, quotient will be 47, remainder will be 1. And if you divide 47 by 2, quotient will be 23, remainder will be 1. If you divide 23 by 2, quotient will be 11, remainder 1. So you keep doing this until you hit 0, and then collect all the remainders. So 95 So if you collect them, 95 will be 10101111 in the binary system. Okay, alright, so let's talk about how to convert a decimal number to hexadecimal. So idea is exactly the same as converting from decimal to binary. Only difference is this time we divide a number by 16. So for example, when you have a number 35 in decimal, and what would be that number in a hexadecimal system? So to divide 35 by 16, and the quotient will be 2, and the remainder will be 3. And if you divide 2 by 16, quotient will be 0, and the remainder will be 2. So the collected remainders, just like previous slide, and then 35 in decimal is a 23 in hexadecimal. Okay, let's take a look at one more example. 95. So what is 95 in hexadecimal? So again, we divide 95 by 16. So if you divide the 95 by 16, quotient will be 5, and the remainder will be 15. And again, if you divide 5 by 16, the quotient will be 0, and the remainder will be 5. So we collect those remainders. And the symbol for 15, a symbol for the numeric value 15, we know is F. So 95 in decimal is 5F in hexadecimal number. Alright, so let's take a look at a relationship between binary numbers and the hexadecimal numbers. Even though the binary number system is very convenient to represent any bit patterns in computing, it's very uncomfortable and inconvenient for humans. When you have so many zeros and ones, we simply cannot remember those types of numbers. So instead of using binary numbers in computing, we use hexadecimal numbers. Okay, hexadecimal numbers are easy to remember, and also especially each hexadecimal number we know represent four binary digits. So basically, you can represent four binary digits, 4 bits, using one hexadecimal numbers. Alright, so let's take a look. So 0. So 0 is a binary 0000. Hexadecimal will be 0, obviously. And the 0001 in binary will be 1, and 0010 will be 2, and so on. For example, let's say 1000, which is 8, and also 1010 will be A, and the 1011 will be B, and so on until the 1111, which is the largest number 4 bits can represent. So 1111 will be F. So as you can see over here, 4 bits can represent a numerical value 0, numerical value 0, and all the way down to 11. So all these values can be represented by one hexadecimal number, 0 to F. So any binary numbers, any set of binary numbers can be easily represented by hexadecimal numbers. All right, let's take a look at the examples, and it will be a lot easier to understand what I'm talking about. Alright, so let's convert a hexadecimal number to a binary first, and then we'll look at a from binary number to hexadecimal. Okay, how about this? BC9. Okay, so B is so instead of changing to a decimal system to binary, we can actually directly change the hexadecimal number to the binary system by just looking at each number. So B, we know the numerical value is 11. Okay, so 11 will be 1011, and because this will be 8, this will be 2, this will be 1, so it is 11. And C will be numerical value will be 12, and 12 in binary system is 1100, because 1 is this is 8, this is 4. Okay, so this will make a C, and 9 will be 1001. So immediately we can change BC9 to a binary number like this: 1011, 1100, 1001. So as you can see over here, one hexadecimal number can be directly mapped to the binary number. How about this one? FFF. F is a numerical value 15. So, and 15, we know there will be 1111 in binary. So FFF in a hexadecimal, it will be 1111, 1111, 1111 in a binary system. Okay, now let's look at a converting binary number to the hexadecimal number. To convert a binary number to a hexadecimal number, what you need to do is we need to collect 4 bits. We need to collect 4 bits from a least significant digit to a most significant digit this way. So when you have this binary number, what you can do is you just collect 4 of them. Okay. This will be a lot easier to convert to a hexadecimal number than changing this one to decimal system to a decimal to hexadecimal. So we can directly convert this one to a hexadecimal number. Okay, so let's look at it. So 0101, so that will be what? So this will be 1, this will be 4, so that will be 5. How about 1111? That's the largest number using 4 bits, so we know it's F. And 0001, that will be 1, and 1010, 1010, so that will be numerical value 11, because this is 8, this is 2, this is 1, B. And then, as you can see over here, there are only 2 bits left. But we can always think there are 2 preceding zeros. So if you have 2 preceding zeros, then it's going to be 0010. So 0010, we know that's 2. So 1010, 11001, 1111, 1010. So is hexadecimal number is 2B1F5. Does that make sense to you? Well, okay, let's do one more example then. How about change the following binary number to hexadecimal, like 1101, 11110. Okay, so in this case, so we just collect 4 bits each. Okay, so that will be, well, this is only 1, so it's going to be 1, and 1011, so that will be, so this is 8, 2, 1, that's 11, so we know 11 is B, and the 1110, so that will be 8, 8, 4, 2, so that is 14. So we know the 14 is E. So 1101, 1110 can be converted to a 1BE in hexadecimal. All right. Okay. How about the following question? What is the largest value you can have using n bits? So let's take a look. So if you have a 1 bit, so largest value should be 1 because you can take only 0 or 1, and obviously 1 is larger than 0. So using 1 bit, we know the 1 is the largest value to be represented using 1 bit. How about 2 bits? So if you have 2 bits, and then we can have a 0, 0, 0, 1, 1, 0, 1, 1. So largest value should be 1, 1. So 1, 1 in decimal is 3. How about 3 bits? And if you have a 3 bits, then largest value would be obviously 1, 1, 1. So that would be 8. I'm sorry, that would be 7. So 4 plus 2 plus 1, so that would be 7. What about a n number of bits? So if you have an n number of bits, what would be the largest value possible? Well, to do that, let's look at the simple calculations using a binary system. Okay. All right. Some binary calculations. In a decimal system, when you add a 9 plus 1, the value would be 10, obviously, but we don't have a symbol for 10. So what we do is we carry to the next digit. So like 10. So 9 plus 1 in a decimal system is 10. How about in a hexadecimal system? 9 plus 1, that would be what? 9 plus 1 will be 10 in numerical value. So in a hexadecimal system, we know we have a symbol for numerical value 10, so that will be A. Okay. So how about binary system? In a binary, 1 plus 1 numerical value is 2. But we do not have a symbol for a numerical value 2, so we carry to the next digit. So 1 plus 1 is 1, 0. How about 1, 1 plus 1? Again, a 1 plus 1 numerical value 2, but we do not have a symbol, so we carry to the next digit, like 1, 0. And then also, when you add a 1 plus 1, and the numerical value 2, but we do not have a symbol for numerical value 2, so we carry to the next digit. So 1, 1 plus 1 is a 1, 0, 0. In the same fashion, 1, 1, 1 plus 1, that will be 1 plus 1 is a 1, 0, 1 plus 1 is a 1, 0, 1 plus 1 is a 1, 0. So 1, 1, 1 plus 1 is a 1, 0, 0, 0. So you can see some pattern here. So when I have an n number of 1, 1, 1, 1, all the way to a n number of 1s, that is actually same as 1, 1, all those n, the n number of n's plus 1 minus 1, because plus 1 minus 1 will be 0. So, but now we know when you add 1 to a n number of 1s, we do know it's going to be just like a 1 and then a n number of zeros, sort of like here. So when we have a 3, 1, 1, 1, and then when you add 1, so it's going to be 1, 0, 0, 0. So 1, 1, 1 all the way to n number of 1s, then that will be 1 and the n number of zeros and minus 1. So this one will be 2 to the nth, because remember we start from a exponent to 0 to all the way, and so 1, 2, 3 all the way to this will be n. Okay, and so the n, the 1 1 1 1 n number of ones, and that will be 2 to the nth power minus 1. Okay, this is the final slide in this video. Okay, in this video, we're gonna talk about some symbols for the numbers. One thing you should look at over here is we use a power of 2, especially for the large numbers. Okay, we all know the power of 10. So, for example, kilo, we know that is 10 to the third power, which is 1,000. But a lot of times in database, or when you talk about data, usually we use a power of a base 2. So the 2 to the 10th power, remember that is a 1024. So 1024 is a little larger than 1000. So sometimes that's why we use a 1024 uppercase K as a symbol, and lowercase k as a symbol for 1000, as you can see over there. Okay, so in case of million, 10 to the 6th power, and using a base 2, that would be 1024 times 1024. So obviously a little larger than the million, but still we use a symbol like M, like a mega. And then for the billion, we use a base 10 again, or base 2. So when you talk about the network speed, we usually use a base 10, but when you talk about data or database systems, many times we use a base 2. So 2 to the 30th power, which is a giga, and then a trillion, 10 to the 12th power, which is a 2 to the 40th, and so on. Up until here, when you discuss the size of the data, about terabytes would be okay, but more and more, as you know, we are collecting tons of data. As we all know, the NSA collecting just so much data, so it has become some controversy. So also in many businesses like Amazon, Google, they're collecting a lot of data. So now I want you to remember one more symbol, peta. So peta is a 1000 times of a tera, or 2 to the 10th power times of tera in case of using base 2. And then 1000 times of peta is exa, and then or 2 to the 10th power times of peta is a exa. So I want to remember these symbols, and also the size of those symbols. So K, kilo, mega, giga, tera, peta, and exa. So you're going to find a lot of literature now using petabytes of data. By the way, 1 byte is 8 bits. Also, sometimes we use a term like octal. Remember, oct means 8, so 1 octal is 8 bits, and 1 byte has 8 bits. Also, why don't you look at these symbols also, like deci, centi, milli, micro, nano, and pico. And but in database systems, we usually do not use these symbols. but when you discuss network speed, we use, or hard disk speed, or processor speed, we use millisecond, microsecond, nanosecond, and these types of units a lot. All right, this is the end of this video about the numbers. I hope you enjoyed it, and please review about all these numbers. So this will be our base for the discussions coming in the future. Also, I will provide an assignment, so hopefully you can successfully finish it. Thank you very much.